Good morning, Dr. T, and good morning, participants. Welcome to the second day of Gyan course. Today, Dr. Ramesh Tigavaruku is going to present in his first lecture about statistical analysis of floods. I request Dr. Ramesh to deliver his lecture.
Thank you, Professor Yadav. I will try to share the. I'll try to share the screen for you first. Okay, so good afternoon, everyone. We're going to talk about statistical analysis of the precipitation extremes as well as stream flow extremes. So I'll provide some basics and then sometimes some advanced concepts as we go on. Am I audible? Everything is okay? Are you able to see the screen?
Yes, sir. You are audible and we are able to see your screen.
Okay, thank you. So the first thing in the last class we talked about, even in the tutorials, is that the data gathering step is the very crucial step where we are looking at any anomalies or outliers or missing data in our data sets. And then, of course, the next step is to see what we can infer from the data we have gathered in different parts of the temporal scale, as well as spatial scale. So when you're looking at spatial and temporal analysis of precipitation and streamflow extremes, there are a number of things which will come to your mind. First of all, frequency analysis of stream flows and precipitation extremes. What we typically do is we take the available data, and then we assign peak design flows based on the return periods. Now, that can be 100-year return period or 500-year return period or 50-year return period, depending upon the hydrologic structure you are evaluating. Of course, there's a risk assessment for every time you are trying to design a hydraulic structure or hydrologic structure, or a combination of both. Most of the time, even in many parts of the world, stationarity is assumed, and very often people do not attempt to check the stationarity. We have recently developed new comprehensive methods to check the stationarity of our data sets so that we can look at whether stationarity assumption is still valid in many of the data sets we look at. The precipitation frequency analysis for different durations is very critical, especially for stormwater management design. And I'm going to throw some perspectives from United States so that you can appreciate what kind of work is going on, so that this way it's important that we share the common experiences between India and United States. So that would be very useful. Of course, I'll also talk about what's going on in the rest of the world and how they are doing. The next topic is analysis of streamflow extremes. We can look at both lower end and higher end. Some of it will be handled in the tutorials in the evening. So I'll be doing all the lectures today. You have another one looking at climate change impacts on hydrologic design, and that will have some component of what I'm discussing in this particular lecture. So therefore, without repeating things, I will spread it over the whole day, or at least the whole session, and then we can discuss. Now, there are two types of analysis spatially. One is at-site analysis. The other one is regional analysis. At-site analysis might involve taking only the data at one particular site. And sometimes we want to do regional analysis. Now, regional analysis can be pooling the data available at homogeneous sites, in the sense you try to establish clusters of the data or homogeneous air regions based on hydroclimatology or any other factors. Once you define these homogeneous areas, then you can pool the data Now, pooling the data has one advantage. You are having more sample points for your frequency analysis. Therefore, your design flood estimates or design precipitation extremes can be derived more accurately because your sample size increases. That increases the confidence in your data set. Of course, pooling has to be done very carefully, because if you don't check the homogeneity of the region or homogeneity of the records, you may be combining different data sets which come from different populations. So you have to be very careful when you combine or when you pool the data. The other thing is looking at joint analysis of extremes. So what is going on is that if there are two or more variables which are affecting your streamflow extremes or precipitation extremes, then you could take those variables and conduct joint analysis. And finally, what we are doing these days in case of frequency analysis, when we see that the climate is evolving. Okay, the main issue is the non-stationarity. So the first thing any data agency or any design agency has to take care is the assessment of the non-stationarity. Once we have the non-stationarity assessed, or if the data has stationary properties, remember, stationarity is not the property of the data, but it is the property of the process which is generating that particular data set. So we got to be careful in how we distinguish stationarity associated with the data or the process. Of course, many people will argue that, well, we don't know much about the process. We are not very sure about the process. The only data we have is the time series data, which might be helpful for us to have some kind of understanding about the process. So therefore, the time slice what we have can be used for assessment of non-stationarity. And of course, we have streamflow projections. When I say streamflow projections into the future based on GCM, that is general circulation models or climate change models, which will involve either dynamic downscaling or statistical downscaling. So we are now getting into a territory where we are introducing more uncertainty into our assessment process or evaluation process. And then the next step is, of course, once you have the downscale projections, then you are looking at what we call the bias corrections, which are again a controversial part of the downscaling process, because there's always an argument that bias correction procedures or bias correction process itself is non-stationary, in the sense that you derive the bias correction approaches based on the historical data, and there is always an argument how you can confirm that those bias corrections will be applicable to the future projections or future scenarios. So that's again a controversial topic in itself. So let's go to the topic, looking at single event and continuous simulation event models. So we have these two models which we use for flood assessments. Single event models are those, for example, rational method, or one of those methods where we just provide one value based on the event what we are interested in, one precipitation value or one intensity or one soil moisture conditions, and then derive the peak discharge. So this is one value. This can be used for design. Again, for more accuracy, continuous simulation models are being used, especially when we are trying to evaluate the floods and generate what we call the flood insurance rate maps. So for example, in the United States, we generate the digital flood insurance rate maps. They are called DFIRMs. So these are available to the public, so public can actually see them and then assess where their house is in particular location to the flooding situation, and then they can definitely work with the insurance agency to decide how much insurance they are going to pay for a particular house in a particular flood zone. So the single event method is pretty straightforward. I will go through the figures, that is much easier. So you start with the rainfall, you do the frequency analysis. Now the frequency analysis will contain a number of statistical steps. You take the extremes of a specific duration, whatever duration you are interested in, and then you look at the possible probability distribution functions that can be fitted. So you look at gamma distribution or generalized extreme value distribution or Gumbell's distribution, depending upon what type of distribution is appropriate for the rainfall for a specific duration. Once you have that, then you ask a question, what can be a 100-year rainfall, what can be a 25-year rainfall, and that becomes your design rainfall. And you take the design rainfall, you put it into your simulation model, and that will give out one hydrograph. Of course, there's another step there before we take the design rainfall and convert that into a temporal distribution of rainfall, because we cannot just get the hydrograph based on one value of rainfall. So you need to probably process through that through a temporal distribution rainfall scheme. And I'm going to talk about that. And once we have that, then you have the design discharge that can be used for design. The other approach is completely different. We take the rainfall data, we simulate, let's say for 30 years of rainfall data if it is available. So you simulate the whole hydrologic model for the 30 years, and then you get your runoff values or discharge values. Then you pick up your extremes, either annual maxima extremes or partial duration extremes. Once you have your extremes, then you conduct the frequency analysis on the discharge data as opposed to the rainfall data. So in this case, you are looking at frequency analysis for your annual peaks, block maxima, or partial duration series if you were to obtain that. Once you have the frequency analysis, then you talk about what we call a 100-year discharge or 500-year discharge, and then you use that as a design discharge. Now, sometimes in our case where we are designing a very sensitive high hazard hydrologic structure like a dam, then we look at what we call the PMP, the theoretically possible maximum precipitation depth. And of course, the definition is very well known. Theoretically, the greatest depth of precipitation for a given duration that is physically possible over a given size of storm area at a particular geographical location and at a certain time of the year. Obviously, this has a lot of qualifiers. So what we do is, if the PMP values are available at some site, we can also transposition to another site where we are taking care of the design. But of course, there are a number of ways you can ascertain the PMP values. There's a Venti-Chaus method, which you can use by increasing the frequency factor value so that you can realize the PMP. Now, that PMP is used in your hydrologic models to get what we call the maximum possible flood, and that can be used for design purposes. So PMPs again are rare extreme precipitation events. This was an event which was recorded by NASA website and so on. This got a very high publicity. This was the first one of those extreme events in 2005 with a record-breaking 942 millimeters of rain in a 24-hour period. Obviously, you must have remembered this event, and this event got a lot of publicity in the United States. And this is definitely a monsoon-related flooding induced by the convective type of rainfall with the moisture coming from the Indian subcontinent. Of course, this is unusual even for a summer monsoon. And this was recorded by the satellite image, and you can see that the amount of rainfall that fell on 26 July 2005. This can be regarded as a PMP. Now, the variation of the precipitation along that, this was garnered by TRMM satellite image, the Tropical Rainfall Monitoring Mission. And you can see that how much amount of rainfall is in progress during the 3 days of that particular event. So that again brings down to the point of what we call the return period, how often an event occurs. Again, the return period is a very sensitive element of design because each type of structure requires a specific return period, and that gives us what we call the exceedance probability. In case of rainfall, both depth and duration are important. So if we know the return period, just a simple example calculations, you can actually calculate the risk, and then based on the simple probability exercise indicating the independence of the event, you can actually calculate the risk associated with a particular catastrophic event. So when I say catastrophic event, it doesn't mean that the structure is going to break, but it's going to damage the structure and that might make the structure invalid or it cannot be used for the purpose it was intended to. So therefore, when you're designing something, obviously the risk needs to be evaluated. Now, risk is intimately connected to what we call the return period. So for example, if you're designing a storm sewer system in a small subdivision in a city, then obviously you have to understand that you'll not be using a 500-year event. You may be using a 25-year event because we will be considering what we call the benefit cost ratios. So this example here illustrates that the catastrophic event happens 4 times in 100 years. The return period doesn't mean that it happens only 4 times or every 4 years it happens. This is on an average, this return period happens once every 4 years. It doesn't mean it will not happen next year. It can happen next year also. So once you have the return period, then you can actually estimate the risk, where N is the design life. So if you put in these numbers for the return period and design life of a structure is around 50 years or 100 years, you'll get a risk factor. The larger the TR period, that is the return period, the lower the risk. But again, would you like to invest so much amount of money in that particular design? So typically in US, what we do is the design return period is defined based on the importance of the structure, the cost of the structure, and the consequences of the failure. And we use typical return periods of 2 to 5 years, 2 to 25 years for storm sewers and detention basins based. Typically, every subdivision has a small detention basin as a non-structural measure, structural measure of trying to address the stormwater runoff. So we actually have a small pond in every subdivision, and we collect the water and then use it either for the local irrigation or controlling the discharge, which can be due to an extreme storm event. Again, sometimes we do use the design storms based on historical data. So depending upon what type of facility you are using, maybe you go with the past existing data as opposed to you doing the calculations based on local rainfall data. Okay, so we do have a comprehensive rainfall database, which is available at this particular server, which is, we call it as a NOAA Precipitation data server. So National Oceanographic and Atmospheric Science, Atmospheric Administration website, where you can actually get your, I'll show you quickly, where you can actually get your data here, sorry. So you can click on a specific, for example, I'm in Florida, so I can click on that, and then it automatically brings the precipitation data for that. And I can actually move this one to a particular zip code. In India, you would say pin code, right? So you can go there and then you can get your precipitation estimates, which are based on actual data along with the confidence intervals. For example, if you're designing something for a 24-hour storm, and you can go here and then go for your 1,000-year, 500-year, 200-year, 100-year, 50-year return period. They also give you the upper interval, upper and lower levels of your precipitation depth. Of course, these are given in inches, so you need to multiply by 25.4, and then you can get your design discharge. Sometimes in case of Florida, we use a 3-day rainfall events because we have frequent hurricanes coming in Florida. So they will take landfall approximately 3 days. So obviously they will dump a tremendous amount of water. So in that case, we have to use a 3-day rainfall. So this is available. Of course, a comprehensive analysis has been done by this agency. We call it as NOAA Atlas 14, and this is used by all the design engineers so that they can actually look at this data. They can actually download the data for all these sites, and you can do your own analysis about stationarity or non-stationarity of your precipitation data. Okay, so that's the thing. And then, of course, we also have what we call the contour maps, which will give us the 2-hour 24 rainfall, 25-year 24 rainfall. This is more of a visual evaluation of the rainfall events, but not necessarily useful for that. So the frequency analysis, which is very straightforward, you pick up the historical data, you pick up the annual maximums for different durations, fit a probability distribution and check. And most of the time, extreme value type 1 is generally suitable. And then if you're using the Discharge formula, you can use the frequency factor, and I'll show you that, and then you can get your average depth. So that's the step. And you try to get the maximum value, fit a distribution, and finally get the intensity associated with a particular return period. So this is your Discharge formula. It is pretty straightforward. Precipitation depth of a particular return period is calculated based on the mean precipitation depth, which is collected from the sample, and K is the frequency factor, and S is the standard deviation of your sample. So as you can see, the equation is dimensionally homogeneous. You can use this one. The frequency factors are available for different distributions. Some of them are derived analytically, some of them are numerically derived, some of them start with minimum sample size of 15, some of them start with any other sample size that can be used. So obviously, if you are trying to do some statistical analysis, the bare minimum sample is 15. Sometimes people will argue that we can do statistical analysis with 7 or 8 samples. Now that is not correct. They are cheating. But of course, 15 is the minimum, and the more the better always in any statistical analysis. So here's an example of a Gumbell's frequency factor you might have seen already. And then typically this is what is used in the United States. And then once you have the number of data, we can locally interpolate and then try to get the best value of the frequency factor for our determination of our specific return period design rainfall. And once we have that, what we do is we develop what we call the intensity duration frequency curves. There can be a depth duration frequency curves also. They are one and the same, but one is represented by depth, the other one is represented by intensity. So that is again straightforward. So you take those values, what you get for different durations and different return periods, and you can actually create this particular graphic. And the main properties are, for a given duration, your average intensity goes up as the return period goes up. And then as the duration goes down, duration goes up, your average intensity goes down, because now you are spreading the same amount of rainfall for a longer period duration or longer period. Okay, so from the Discharge curve, you can actually get different values of your rainfall depth for different return periods, and you can actually generate this curve. This is an example from Florida. These curves are available to engineers so that they can use it for design purposes, and they are given for different return periods. So as you can see, this is a log scale plot so that you have the values. The minimum values of time is 8 minutes. Anything less than that has to be either interpolated to extending these curves this way, or you could take the same intensity what is available at that point, that is 8 minutes. Okay. Now this is very ideal for your storm sewer design, because you are going to use the intensity values for your based on the time of concentration calculations in rational method. So obviously this is a very useful tool when you're trying to develop your storm sewer design. So in case of storm sewer design, obviously you know the design rainfall based on the selection of the return period. So you'll get hold of that intensity. And once you get the intensity and you know the duration, particularly what you are looking for, you can get what we call the storm depth. Now, once the total storm depth is available, we have to transfer that into a time distribution of the rainfall. How do we do that? It depends on the region-specific time distribution curves, or the United States agency, which is referred to as the NRCS, Natural Resources Conservation Service. They provide these synthetic distributions which are valid for the entire United States. So we could use them to get from the total rainfall depth to the intra-storm values so that we can use it in our simulation of single event models. Now, of course, these are not continuous event simulation models, because continuous event simulation models will require information about the soil moisture and other parameters. A very good example is the Sacramento soil moisture accounting model that is being used in HMS and other softwares. So that one uses information about soil moisture and other things, and it's a continuous simulation model from one time to another time step. We continue and we try to estimate the maximum peak discharges there. Now here we are using single event model, therefore we have to use one depth, and that depth translates into temporal distribution of the rainfall, and once we have the temporal distribution of the rainfall, we feed it into a simulation model. So obviously we are interested in something like this. So for example, either for 24 hours or 48 hours or 72 hours, we need this one to be plugged into our simulation model. So there is a need, of course. One rainfall value will generate this one, that is one value of runoff. But if you provide a hyetograph of rainfalls to a simulation model, you'll get your discharge, which is very critical for us. So therefore, you cannot stop at the frequency analysis of the rainfall events. You have to go to the next step of taking that particular rainfall depth and translating that into your intra-storm duration rainfall depths, so that we can take that hyetograph and put it in our hydrologic simulation model. So how do we do that? There are a number of synthetic distribution, rainfall distribution curves. I'm not sure if these are available in India. Have they developed for any sites? Do you use them? This is the question for you. You can answer if you know that. These are routinely used in United States. We call it as rainfall distributions. And there are two forms. One is the dimensionless form, where we call it as the ratio of the time over the total duration to the precipitation over the total precipitation, so that both of them remain dimensionless and they vary between 0 and 1. Most of them are S-curves, and the maximum intensity happens somewhere in the middle of the precipitation time interval. So from this one, based on the ratios of the times, you can actually read the PO or PT values, and from PO or PT values, you can actually calculate the cumulative rainfall. From cumulative rainfall, you can actually calculate the incremental rainfall. So these are the distributions, which we call it as dimensionless form. Then we have what we call the semi-dimensionless form. These are dedicated for specific hours from 0 to 24 or 0 to 48 or 1 hour or so on. So the x-axis is always having some kind of dimensions. That is basically the hours. And the y-axis is the ratio of the precipitation until that time divided by the total precipitation. So what we are getting is a ratio of no dimensions. So that way the y-axis is always between 0 and 1. So using that information, we can actually derive those time-based distribution of the rainfall for our single event simulation models. So once we get the hyetographs, we have to look at what is going on with your hyetographs. Is there an early increase in the rainfall? Is there a central peaking or a late peaking? It is very important because that will affect the runoff floods. Okay, central and late peaking storms were found to create significantly larger peak flows than early peaking storms. You can guess the reason why. And then of course these distributions are changing with respect to climate also. So that means those distributions which are derived long time back based on rain gauge data may not be valid for future because things are changing with respect to time. So here's a visualization of early peaking, central peaking, and late peaking. So it is expected that more peak discharges are possible in case of central peaking and late peaking. And anybody can guess what might be the reason? The reason is, anyone? You can use your microphone and say it if you want to say it. So ideally, you will have more higher peak discharges for central peaking and late peaking storms. That means you can see the figure here. So what is happening here is that because of the soil moisture buildup, as this storm goes up and then recedes, you will see that this will result in more flooding, because water is not able to infiltrate into the ground, and then you have more flooding. Similarly, the same situation, more antecedent soil moisture before the peak event, because the soil moisture is building up, and that will cause more flooding. So as I told you, we can construct this, and in United States, the Natural Resources Conservation Service provides us these 4 distributions. Even though it's very gross approximation, they may not be applicable for the entire United States very well or valid, but these are already provided to the users. So we could use these distributions for our calculations in single event models, and these are already embedded into different hydrological simulation models, for example, HEC-HMS and TR20, TR55, and these are publicly available. So basically, we take the rainfall depth from our frequency analysis, we put them into these distributions, and then we get our intra-rainfall or intra-event rainfall distributions or values. So this is how these values are available. For example, I'm living in Florida at the bottom, so Miami is somewhere at the down. So this area, we have to use a type 3 distribution. And as you can see, there is some commonality in the tropical region. This is Texas and Gulf of Mexico. So we use this type 3 on the eastern seaboard, and on the eastern side, where the hurricanes come from this side, you are the analysis suggests that type 3 is appropriate for this region based on the rainfall data they have used. For the rest of the country, type 2 is possible, and then type 1 on some part of California, and type 1A, and type 1 for Alaska, and so on. So this indicates that obviously you can see that this is a very coarse scale provision of rainfall distributions, which may be or may not be accurate, but nobody is stopping you from developing your own rainfall distributions based on the locally available rainfall data. So these are 4 types: type 1A, type 1, type 2, and type 3. As you can see, all of them are S curves, that is S-shaped curves, and they are all for 24-hour duration. Typically, a 24-hour duration storm is used for many design purposes, so therefore these are built for 24-hour storms. And you can see that the maximum intensity typically occurs in the middle of the storm for some of the distributions. Wherever there is a slope of the line is the steepest, that's where you can expect a sudden increase in your rainfall amounts. And most of these distributions are either early peaking or central peaking, indicating that you might have a good amount of rainfall distribution in the early part of the storm, and that might also affect your peak discharges. Then we have another distribution which is commonly used. I told you about dimensionless distributions. These were created by Huff in 1967, long time back. Of course, we don't use them, but the idea is to develop non-dimensional distributions that can be used for design purposes. These were developed for Kentucky, Illinois, and Indiana, but again, the concept can be repeated to other states so that we can use these distributions. Now, the interesting thing is that how these distributions are changing with respect to climate change and variability. And of course, we have the first quartile, second quartile, third quartile, and fourth quartile. It basically suggests that if the maximum intensity happens in the first quarter of the storm, we call it as first quartile, and so on. So if it happens in the second quartile, second quarter of the storm, we call it as second quartile. So remember, we have seen the intensity, duration, frequency curves. Here I'm just showing the other version, that is the depth, duration, frequency curves. And based on our oscillations, we have an Atlantic multi-decadal oscillation that affects our temperature and precipitation patterns in Florida. It is something similar to your ENSO, the El Nino southern oscillation, and that basically is a 2 to 7 year oscillation, whereas this one is multi-decadal, approximately ranging anywhere from 25 years to 35 years, and it will have both warm and cool phases. Now you can see that when we try to evaluate the data from just the cool phase and just the warm phase and the entire data, sometimes your depths are higher in the warm phase, sometimes your depths are higher in the cool phase, and the entire data stays in the middle. So that indicates that even the temporal distributions of the rainfalls, the intensity, duration, frequency relationships are changing with respect to climate variability, not only climate change, climate variability. So now that begs the question, are we going to change our design? Are we going to use higher depths because we expect this natural cycles to be happening? That is the question. And of course, being on the conservative side, you should be using higher depths for your design purposes. In this case, the intensity was fitted with what we call the generalized extreme value distribution. So obviously, the rainfall is one of the factors where we can do statistical analysis, either for continuous simulation models or single event models. Single event models will require analysis starting from the raw values and extremes, and then going through the process of intensity, duration, frequency relationships. So when we are looking at frequency analysis for peak discharge design, depends on the type of hydraulic structure we are looking at: bridges, levees, open channels, and culverts, and so on. Again, it depends on what type of structure you are constructing, what is the benefit cost ratio, and what will be your return period that should be used. For minor structures, you can go from anywhere from 2.5 years to 50 years, but medium-sized structures, 100 years, but dams, dikes, and so on can be much, much larger. Always remember, when you are talking about a 1,000-year flood, there's a lot of uncertainty associated with that because you only have probably, 100 years of data or less than that. So you're trying to do a humongous amount of extrapolation starting from 100 years to 1,000 years. So again, the values which you get for 100 years. Yes.
So sorry to interrupt, but before going to frequency analysis, I want to ask a question on the rainfall.
Sure.
As we have discussed the partial duration series.
Yeah.
Yeah, in the partial duration series, as per the VT-Chow technique, if I have to go with that, it says that arrange the data in descending order, and if I am having a 50 years of data, so the first 50 values I should take, and the 51st value, 51 value will be the threshold.
Okay.
But it also says that the event should be independent events. So in this case, if in case of Mumbai, if 25th July, 26th July, and 27th July, these 3 days, if we have the extreme events, and if I want to consider, and all these 3 values are above threshold value, so can I consider all these 3 values?
No. So whenever you are doing any type of statistical analysis, the traditional statistical analysis, not the spatial statistics, but whenever you are doing traditional statistical analysis, independence is very important. So that's the main problem with peak over threshold analysis. So when you have events which are very close by, like 3 days or 1 week apart, in case of peak over threshold analysis, the independence cannot be guaranteed. That's so the 2-3 values you are getting are part of the one series. So in that case, you cannot use those 3 values as part of your peak over threshold analysis, because the independence, which is the prime important assumption of your traditional statistical analysis, especially the frequency analysis, is gone out of the window. So you cannot use. So that is definitely a situation that comes often, especially for rainfall peaks. But if it is stream flow peaks, if the peaks are having a lot of time in between them. For example, the peak flow, one peak flow happened in May, another happened in September. Maybe the hydrograph has receded and then went up again because of an extreme event. Then in that case, you have what we call the independence. So in that case, you can take the independence. For rainfall events also, there is a concept called inter-event time definition, IETD. That means if there is a long enough time duration between two rainfall events, they can be considered as separate events. So if that IETD typically varies from 2 hours to 16 hours or 18 hours and so on. So if two events are happening within that IETD time, they will not be independent, and we cannot consider them to be good for our frequency analysis. That has answered your question?
Yes, sir. Thank you.
Yeah. So in case of peak discharge estimation, we can do a frequency analysis, or we can do what we call extrapolation analysis. When I say extrapolation analysis, obviously, I'm not dealing directly with one site. I'm dealing multiple sites. So in that case, either we do area-based analysis or regional analysis or regression analysis, so that we can get to the point of getting the peak discharge. The indirect method, which we have already discussed, is called the design intensity method or design storm method, depending upon how you use it. Design intensity method is nothing but your rational method. And design storm method is trying to get the storm depth and then use it in your simulation models. So obviously, we need to do a lot of EDA, that is exploratory data analysis, to make sure that whenever we are doing a time series analysis or frequency analysis based on discharge depths, annual maxima, and so on, we need to make sure that we need to consider the exploratory data analysis. So this is what we were just discussing, the annual and partial duration series. Depending upon what is your block maxima, you pick up the extreme values. If you are looking for droughts, you go below the threshold, and then of course higher for the threshold. So again, every time you are taking any values above threshold or below threshold, the independence is very important. In US, we use the concept of water year. We can also use calendar year, because all the data is available. So you can go ahead and use that. In this case, the water year is defined from October 1st of any given year through September 30th of next year. So most of the peak values provided by United States Geological Survey are based on the water year basis, because they use it for their reporting purposes. And then this one is called a hydrologic year and discharge year. One of the reasons they use this water year concept is that you're not breaking in the middle of the year as you do in your calendar year. So you are trying to incorporate all the seasons, and then you're trying to get those extremes within one water year. So a number of EDA approaches can be done, that is exploratory data analysis. So anytime you're trying to do a frequency analysis, the first thing you have to do is look at your time series, look at any breaks in the time series, look at the trends and stationarity in your time series, look at any change points in your time series. Once you have established non-stationarity, try to understand what is the issue with that, in the sense, is there an attribution to why that changes in the stream flows are happening. Now, one important thing you have to do is, whenever you have stream flow data or rainfall data, you can do a autocorrelation test to see if there's any dependence over the years. So that means there are no cycles of continuous floods and continuous droughts. There are no cycles like that. So the best way to do that is to check autocorrelations, or you can do a runs test. Runs test is available commonly in every statistical software. For example, S or R or MATLAB, runs test is available. So the runs test can tell you whether your data is in fact random. If the runs test tell you that the data is not random, then you have to do further exploration of what is causing the non-randomness into your data set, and then need to find out the attributes. Many a times you can look at your stationarity of your data by just splitting the data into 2-3 halves, and then looking at the statistical properties. Have they changed over time or not? So if you are looking at a frequency analysis and you see a trend in the data, that indicates that's non-stationarity. So there is a possibility that your defense of using this historical data for frequency analysis is little debatable, because there is a trend in the data which is statistically significant. So in that case, you have to justify why you are considering frequency analysis under a stationary environment, when the data in fact shows that the whole process is non-stationary. You are seeing an increasing trend in the data. You're also seeing an increasing, you are also seeing a changed values of your parameters or the distributions. So therefore, you have to be very careful when you're doing frequency analysis, because frequency analysis is based on the assumption that past is reflective of future. So things have been under a stationary environment, which is not possible with cases where there's a trend in the time series data. We'll look at those examples in the evening. I have different types of data sets from India and US. We can look at that. So again, as I said, you need to look at the time series data and see if there's any linear trend, periodic trend, change in variation, variance, and then change in average. So the different types of series can exist, which can point to non-stationarity. Typically, the distribution can be checked by histograms. The problem with histograms is that there are no good guidance about the number of bins. So if you use the wrong number of bins, the visualization may affect with the way you interpret your histogram. So even today, we don't have a real thumb rule. What should be the size of the histogram bin, and how many bins we should be using for a specific data sample? How many bins we should be using? There are some new developments from Japan. There are a couple of papers who have come up with the best optimum size of the bins and the number of bins, so that we can effectively show the distribution more accurately than by arbitrarily selecting the number of bins by these thumb rules. So there are several thumb rules which are available. Some of them work very well. Some of them are completely useless. It depends on the data. So we need to be very careful about that. It should be chosen from judgment and the two less. Sorry. Any question? Okay. So we can also look at the distributional characteristics of your data sets, which is pretty straightforward. All the four moments: mean, variance, skewness, and kurtosis. These are the four properties which we use. Then you can look at the CDFs, or the probability density functions. So as I was telling you, these are the four moments we use, like the ones which we use in civil engineering, the moment of inertia, similar to that. First moment, second moment, third moment, and fourth moment. These are very critical for us to understand that the distributional characteristics are not changing with respect to time. So if only mean is preserved over the time intervals, we call it first order stationarity. Then we have the second order stationarity, and strong and weak stationarities, and all kinds of definitions available for the stationarity. But again, at the end, you are going to effectively evaluate the available time series for changes in the distribution. So here are some examples of the moments you might have seen in any statistical textbook: mean and variance, and skewness, which is the visual evaluation of the fits. Here's an example of streamflow data, and log Pearson 3, very commonly used in United States, gamma, normal, and log normal. I do have some issues with normal distribution being fitted to our data, because normal distribution states that there's a negligible amount of probability for negative flows, because normal distribution moves from -infinity to +infinity. So there's a problem with that. So again, the other distributions are valid. This is a visual check, but you can also do a thorough check of the distribution fit for the statistical fit for the data sets using hypothesis tests. and then finally conclude that the data follows a specific distribution, so that then you can make inferences about the peak discharges for given return periods. The other one is the plotting position methods, which are very common. We use them all the time, and there are different plotting positions available depending upon what type of distribution you think is more appropriate. They are named after different researchers. In that formula, what I have just showed you, those are the coefficients for A. Again, some people argue that one is better than the other. Some use a standard Hazen plotting position for all our empirical cumulative distribution functions or for quantiles. Normal distribution, again, the problem with that is its use is inappropriate for positive variables. Discharge and precipitation are positive. Of course, temperature, we can use normal distribution. So typically we prefer log normal distribution, which fits very well with many of our positively skewed distributions. Then there's a 3-parameter log normal distribution, which will help us to get that shape a little bit better compared to the previous 2-parameter log normal distribution. Then we have extreme value distribution, which is used for extremes. This can really help us to model our rainfall extremes and streamflow extremes. Then there are type 1 and type 3 and type 2. And there's a generalized extreme value form, which can cover all the 3 distributions, so that we can use one generic formula. Depending upon the parameter values, we can claim that it is either type 1 or type 2 or type 3. Gamma distribution is very common for rainfall extremes or annual rainfall values, annual rainfall totals, and very well fitting for even daily rainfall values, as they are positively skewed distributions. Pearson 3 with the 3 parameters. This is also common for many discharge values. We use them for fitting the distributions. And there are, of course, other distributions which commonly appear in statistical literature, logistical and normal, and then Pareto distributions, depending upon what type of parameters you're using. Some of them were used for characterizing precipitation extremes. So typically we use the method of moments. This is a simplest way of estimating the parameters of the population based on the sample. What we do is we calculate the sample parameters, and then we say that these are equal to population parameters. Remember, population is never available to us. So we are making inferences about the population based on the sample data. So of course, in hydrology, we can never expect to have population. We can only have a sample because the most of our data extends only up to 150 years or 200 years. So the other approach which is most commonly used is the maximum likelihood estimate, MLE. That's available in all statistical softwares. This one will produce more robust parameter values, unbiased, so that we can use that in our calculations. So that's the method of moments, where we equate the sample moments to the population moments. That is first moment, second moment, third moment, and so on. Whereas the maximum likelihood method is a little advancement. It's a very intuitive and method for estimating the parameters, where it maximizes the maximum likelihood function, which is nothing but a product of all the probabilities when specific parameters are used. So it's like saying that the best parameters which will maximize the probability of characterizing a particular event accurately. So in that case, when you maximize this function by applying what you call partial derivatives and equating to 0, like our typical maxima, minima way of calculating the parameters of a function, what we do is we equate them to 0 and then we estimate the parameters. So this is by far the best way of estimating the parameters. Of course, there are more complex and more better estimation methods, which we call L moments. Okay, L moments are linear moments, and this was invented by people at IBM working on trying to look at this very small samples. When you have very small samples, you have issues with estimating the parameters correctly because you have a lot of bias. And what they have suggested is that the L moments can be beneficial because of their properties, so that we can estimate the parameters much better when the sample sizes are very small. But when the sample sizes are large, if you use the maximum likelihood method or L moments, they are one and the same. Okay, so there's a little more complex theory behind how these parameters are estimated as a linear functions, and then finally we have these values, and that can help us for our estimation of the parameters. And I'm going to show you in the evening how we can estimate parameters for different distributions, and then how we can use them for our calculations. So when it comes to spatial analysis of peak discharges, we'll go through this to understand. For example, your design point is QD at a location where you want to estimate the peak discharge. So in this case, you have information about QB, that is at that particular site. You have information at QA, that is another site, but you don't have information at QD. So one way, and you have precipitation in the watershed, one site, and there's another one called QC. So you have three measurements, QB, QA, and QC, and a precipitation point. So you can easily imagine that if you want to estimate the peak discharge at D, probably you can do area-based regression, or just simply area-based analysis, so that you can get the D value based on the values at B or A, or you can do what we call regional analysis. So, for example, if you want, if you have long-term values at D, you can do frequency analysis. If you don't have long-term values at D, you have to do area-based analysis using A and B, A or B values. If you only have values at C and other areas, you can do regional analysis or regression analysis. But if you have precipitation, you can go ahead and go for the design intensity method or design storm method, which I just discussed. Okay. So we can check probability functions, distribution functions, and how they fit very well. And for example, I already discussed, we have three to four distribution methods which we are common, and log normal, Gumbell, log Pearson, and we can check how well they are doing by probability plots. We can develop probability plots for each of these distributions and see if they fall on the straight line. This is an example of a normal probability plot paper, log normal probability paper. And then on a probability paper, the CDF should plot as a line. Here's an example of St. Mary's River, McClenny. These are the peak discharge values, 1 value per year. And you can see the histogram shows it's positively skewed. More bins, then we can use Excel to come up with the histograms, or we can do the probability plot, and you can see the deviation from the straight line. So if I apply the logarithmic transformation, more or less the values appear. This is your empirical CDF plot of the peak discharge values. Log transformed value kind of follows the histogram, and this is based on the raw data and the Bayesian. But when you apply the logarithms, you see that the fit is getting better. We can check if the fit is better or not by using what we call a Kolmogorov-Smirnov two-sample test, and check, in fact, the distribution follows the hypothesized distribution. This is our Venti-Chow's method, which we have already discussed. And we can use frequency factors like this for normal distribution, log Pearson 3, Gumbell, and we can actually calculate the return period or probability of exceedance. In US, we use a method called Bulletin 17B for our log Pearson 3 distributions. And then because the skew is estimated from the sample, what we do is we try to improve the skewness estimation using generalized skew coefficients, which are available for the entire United States. We make the corrections for the regional values so that we get improved. I'm not going to go to this procedure, but this is a standard procedure which is available. let's go quickly to the regional analysis of peak distribution we were talking about. So if you're interested in QA or QB, can be related to based on areas. Once QA and QB are related by areas, of course, you can solve for A and B regression coefficients. You can actually solve for QD by just applying the same coefficients but changing the area of watershed of D. That can be done. And here's just making an assumption for one of the parameters equal to 1, and then solve the other one for A and B, and then finally getting back to QD. So if you're interested in trying to find out peak discharge for a specific return period based on information that is available regionally, that is spatially, A, B, C, and E, and F, what we could do is, for example, if you have multiple watersheds in a region, they are homogeneous to some extent, they have the similar land use patterns, they have similar hydroclimatology, then we can do what we call a regional analysis. Of course, you need to be careful what type of watersheds you are picking up. So you pick up all these watersheds, and once you have the information from these watersheds, the only thing lacking is for D. So we are going to estimate the peak discharge at D by using this procedure. So first, what we do, we go to the different areas where we have data, A, B, C, and E, and F, and then we get the return period ratios with respect to Q2. For example, we take a base flood frequency of two years. So we get 100-year discharge divided by Q2 and so on. So we get all these values, and the last value is 1. So note that the D column is missing because we don't have data at D. Okay, that is done. And the next one is we try to plot a relationship or establish a relationship between the two values and the return period. We just got all these ratios, and then we establish 2, 5, 10, 50, and 100. We establish a relationship. Sometimes you might find some outliers, so that's why I'm saying filter and fit, and try to fit the best possible regression line. Of course, I'm exaggerating there, but you'll find a reasonable fit if the watersheds are in the same homogeneous area. So once that is done, then we fit a relationship between area and Q2. So that will help us to establish some kind of relationship. I'm just plotting it as a linear, just for the sake of simplicity, but you see D is not there here because we're not going to have a relationship between area and Q2 because we don't know Q2 at D. So we are going to have this relationship. So now the final way of finding the return period for QD, peak value for a given return period for QD, is basically you select the return period. Let's say you select 30 years. You select that, and then you get the QT over Q2 ratio. So you get that value. And then we know the area of D, we get the Q2. So we got this and we got this. We multiply these two, we get the Q2. So very intuitive procedure for regional analysis of missing peak discharge values. And we are taking information from the nearby areas, trying to fit the regression lines, and then finally ending up in the best possible estimates for the ungauged basin. In this case, QD is ungauged basin, and we're trying to estimate the peak discharge value for a given return period. So we don't have to sacrifice information even for the return period also. The design intensity peak discharge method is very simple. You get the design intensity from an IDF curve, put it in a peak discharge model, and then you get your peak flood, which can be a rational method. And what I'm trying to show here can be something like this. We know the watershed area, we know the intensity, we know the rational coefficient, and K is the conversion coefficient, so you can get your peak discharge. The design storm method is different. What we do is we take the design storm depth, we pass it through the rainfall distribution model, that is the temporal distribution model, get the hydrograph, then put it in the hydrograph in a rainfall excess model so that we get the effective rain, and the effective rain can be put in a runoff hydrograph model because we have this SCS unit hydrograph methods which can generate our peak discharge hydrographs. So before we close today in this topic, The next 10 minutes, I'm going to talk about spatial dependency and joint probability analysis. So many times we see that rainfall data is linked with the peak discharge data. So the first part is, can we do some kind of dependency analysis? So the idea is that the timing and the spatial distribution of extreme precipitation and peak discharge events along a conveyance capacity, along with the conveying capacity of a hydrologic structure in a basin, determine the severity of your flooding. So if you have a conveyance structure like a canal with a gate or something like that, right? So in that case, the timing and the spatial distribution of precipitation extreme will define whether the conveyance system can have a good handle on the peak discharge which it is able to realize. Okay, so therefore what we have to do is we need to understand how the extreme precipitation events happen, and of course we have to look at the antecedent soil moisture conditions and any regional relationships, and then understand the risk associated with your hydrologic structures. So frequency analysis can be done, may not help in the assessment sometimes because we are not doing a joint analysis, so it's better to use what we call joint assessment. Okay, so these are some of the objectives. So how do we model the temporal distribution of precipitation of events linking to peak flooding events? Maybe look at last 10 to 50 years from the gauging station selected. Look at different temporal storm events, meteorologically homogeneous areas, critical evaluation of the pathology of the storms, the type of the storm which is coming in. Is it extratropical, convective, frontal systems, and so on? Because cyclones or hurricanes may dump a tremendous amount of rain that's going to affect your peak discharges. So this is what we are going to do in terms of the discharge assessment with your precipitation. So I'm going to go quickly here. So what we do is what we call a dependency analysis. I think this is better in terms of the explanation. So you have a peak discharge happening here. So what we do is, this work is published, by the way. So 10 days or any number of days, you go backwards and you sum up all the precipitation amounts. So I'm going to sum up the precipitation amounts 10 days backwards from the peak discharge that happened that year. So I get that for every year. And I can also introduce a lead time, for example, like this, so that I will not count the lead time. I will only count from this particular point backwards, so that this gives me some kind of a lead time to assess the peak discharge. What is the probability of getting a higher value of peak discharge above this threshold when we look at that? Again, we can also look at what is the difference between when the peaks are occurring and when the rainfall peaks are occurring. So this is the temporal difference of the occurrences between. So this kind of helps us to understand how the basin is reacting, how fast the basin is reacting to a particular rainfall event that happened 10 days back or a few days back. Okay, so once you do the dependency analysis, we have established relationship between accumulated rainfall and discharge. So we can do all these checks. For example, you take accumulated rainfall of 10 inches, let us say. You go up and then you get your Q value. Now that Q value can be compared with your design discharge, which you have already previously used for that particular canal. So if the design discharge, if the Q you get is more than design discharge, probably you have underestimated the rainfall. You have overestimated the losses from the rainfall. That means you are saying more water is going into the ground, so I don't have to worry about that. But maybe it's wrong because the climate has changed, the land use might have changed. If the Q value, what you get from this figure, is less than the design discharge, then it's okay, it's adequate. And Q is equal to design discharge from this dependency analysis. Maybe it happens, but it's very rare that it is exactly equal to the design value. Similarly, we can do the same comparison coming from the other end. You start with the discharge and then go back to your rainfall. Are you using the right rainfall for your design? So that means if the rainfall is greater than the design rainfall, maybe you are underestimating the rainfall abstraction. If it is less than the design rainfall, it's probably your rainfall abstractions are overestimated. But R is equal to RD, that rarely happens, but it might happen. So these are some things which throw light on your conveyance capacity, the level of service, we call it in United States, the level of service the hydraulic structure is providing you based on the new changes in your climate. We also look at the synthetic distribution. Some time back I showed you how they change with respect to time. So you can see that this is a synthetic distribution which is provided by a local agency, and this is what we see based on the climate, new climate. So again, there are so many changes that we need to readdress these curves. That means reevaluate this rainfall distribution curves under evolving climate. This is for the 3-day, because remember I told you 3 days is important for us because we have hurricanes which go slowly on the land and dump tremendous amount of rainfall. So the joint probability analysis is very interesting, where you take the accumulated rainfall and the discharge. You can do copula-based methods, which were discussed by Dr. Mighty yesterday, or you could do a simple multivariate normal distribution approach, where bivariate distribution approach, which I'm going to discuss. So sometimes the normality is a requirement because you're looking at bivariate normal distribution. So we do a transformation. We take the data of rainfall, and this one, here's an example which we have used in some parts of South Florida where we have a lot of structures. And here's the hurricane history. These are the pathways by which we get hurricanes every year. These are from 1951 in the Atlantic, or this side. All the paths which have gone through until 2018. You can see how many hurricanes we get every year. These are the cyclones, basically. And the extreme precipitations are also higher for different precipitation durations. And this is our lag, what you call dependency analysis. So that means you see the lag days and the correlation between them. And I'm going to show you this example here. So you see here 0 days, 1 day, 2 days, 3 days, and now going up to 10 days. So you can see different correlations suggesting for this particular basin how fast it is responding to discharge, and there's a relationship between peak discharge and accumulated rainfall over the past few days. Some of it is completely original data, some of it is combination of hurricane related data and non-hurricane related data. Hurricane means basically a cyclone. And the temporal distribution, how the temporal distribution of the differences between when the precipitation event occurred and when the discharge event occurred. So you can also look at that. These are the transformations for us so that we can achieve the normality. And this is the joint distribution of accumulated precipitation and discharge. And this is the exceedance probability. The previous one is non-exceedance, and this is the exceedance. But the conditional probability is more interesting. This is the conditional probability. So for a given amount of rainfall, what is the probability of exceeding 500 feet cube per second discharge? So that means we can find out these probabilities, which are very beneficial for operational perspective for emergency management. We can say that, okay, if you are having 6 inches of cumulative rainfall before this day, then we can say what's the probability that it will exceed this particular discharge. So that will help us. So the joint probability analysis is a very good tool which can be used more effectively in copula-based methods, but we are using a simple bivariate normal distribution method so that we can make statements about exceedance probability and non-exceedance probability, and that really helps us. We can also use it for forecasting, alerts, and so on, because we can use the lead time I discussed. Okay, and these are some of the things, and I think that's what I will end here. We are pretty close to the ending point of our first session, and please make sure that if you have any questions, you can definitely ask me in the session when we do the tutorials in the evening. Is that okay?
Yes, sir. Yeah. Yes, sir. Yeah. Please.
I know there's a lot of material to digest, but keep all the questions you can email them, or you can, today in the evening when we have a lot of time for our tutorials, you can always pose those questions. That will be more interactive.
Anyone have any question right now? Okay, so if you have no question, then we'll break here for 15 minutes and we'll resume the second session at 5 p.m.
Okay, so I might be a couple of minutes late. I have to grab lunch and then come back. Okay.
Okay, sir. Okay, so so shall we keep it 5:10?
Yeah, I mean, just 5 minutes more, maybe. That should be fine.
So
I just need. Give me 1 second. I'm trying to see how. Okay. Okay, I want to see this one. Stop sharing. Okay, so yeah, 5 more minutes should be fine. And I will join immediately. I just grab something and bring it here.